Thanks for the introduction. Yeah, then we can start right now with the topic. So, at first, why do we need synthetic data? So we will start with the first introduction of general optic quality control. As you all know, optical quality control helps us very much to automate processes to... Let's have a look. So, perhaps it's better from this side. So, optical quality control helps us to automate processes, to reduce human effort, and give us documentary content to show what has been inspected and controlled. And deep learning is one way of implementing such optical control for automatic evaluation. Deep learning depends on, at least if we use supervised methods, on a large amount of data. And to generate this data or to achieve this data with real-world data is quite cost-intensive. You need a lot of human labor effort, you need perhaps a lot of energy costs, as we will see in the example we will have in this speech when it goes about welding seams, which are, as for sure, cost a lot of energy to produce these welding seams. And if you want to have a deep learning approach, then you need also a lot of scrap, because you don't to have only okay parts will not be sufficient for a deep learning supervised approach. So all in all, we have a lack of data. And to compensate this lack of data, we can use synthetic data generation as approach to compensate this lack of data. So there are different ways of doing this. One is model-based software simulation, computer graphics way of doing it. For example, as you see it in this traffic scene by NVIDIA, or for logistic approaches, or from our institute, from Fraunhofer IPA, in this left corner, where we have a 3D model which will be adapted, and using rendering tools we see different kind of scratches. So this can be used for quality control. Let's say the other ones, like this traffic scenes or this logistic image, looks nice but is perhaps not realistic enough. So we have to make a big difference between realistic images and nice to look at images. Nice to look at images are produced quite easily these days, but images which are giving us pictures which looks very similar, like the one we would get out of the camera, is quite difficult to achieve, or more difficult to achieve. And that's exactly where we like to point our solution out. But at first, in contrast to this simulation-based way of doing it, there are also, as you all know, generative approaches. Generative AI is, I think, one of the biggest topic these days, one of the biggest growing technologies, as you are all aware, with DALL-E or for sure ChatGPT. And you see here, for example, a lot of human or human-like pictures, but none of these persons really exist, as you perhaps have already seen on quite other homepages or in the media. So these generative approaches can be used to generate new data, as we know. As you all know from DALL-E, you can use text as input to generate different kind of images, like an astronaut riding a horse. But this is perhaps not ideal for the field of quality control. To describe defects like cracks or bumps or whatever by text, and also the localization is quite difficult and a lot of effort. Perhaps it's more useful to use semantic masks like we see here. So we have here the original images, we have here a semantic mask which is already adapted, and this semantic mask is then used to produce the synthetic image. And so it's much more intuitive, much more easy to use than we use just text as input for our image generation. The main example I would like to show in this speech is the control of weld seams, because it's a very good example, because it's obvious that it costs a lot of energy if you use arc welding, or if you use lasers to produce these welding seams. It costs energy, it costs material, so you have a lot of cost aspects and taken into account. So let's start with the amount of images we had in the beginning. So we had here 202, I think perhaps it's on the next slide, more representatives. So we have 202 images acquired, which is when we use what's quite common for evaluation and to recognize if we have overfitting or any kind of misleading data leakage problem, to separate the data sets in different folds. And then if we take a look at the different kind of folds, we see that we have for the two kind of defects which we are focusing on in the also published paper and in this presentation, is quite underrepresented. So we have for the first fold in this welding spatters only 19 examples, which is far too less to get a reliable supervised learning model trained. And for porosities it's even worse, because we have here only 9 examples of these kind of defects, as we have not only to split it up in the folds, we have also to split it up, as you all know, for training data, validation data and test data. So now you see, sorry for that. Now you see already how these images can be generated. We have on the left side the original image, on the middle side we have the semantic mask, which is now adapted, and you see how it is rendered in the real time. So we have not speeded up this image, this video. It's really the time which is needed for generating the image. And it's not just a copy-paste, it's really that these defects are fitting to the environment. So it's try to produce the model we have trained, the pictures as like they would be produced in the real world with the real camera system we have set up. So, but we don't do this just to have synthetic data. The main aim is that we get a better supervised learning model, a better quality control in the end. So now we have to check if we have really a benefit out of these added synthetic data. For measuring this, we use the intersection over union, or the mean intersection over union. As you see in this upper left corner, the intersection over union is defined with this graphic, let's say. So we have, let's say, this is the position, the ground truth. Here we would expect the data, the bounding box for it, and the other rectangle is the area where the model has said the defect is. And then we take a look at the intersection of these two rectangles, put this in the denominator, I think it's the English word, and the sum of these areas in the divided by the sum of these areas. So this is intersection over union, and we use this as measure. The more the two rectangles, the ground truth and the detected area fits together, the more they lie in the same position, the better we have localized all the defect. And then if we take a look at the intersection of a union, how does this change? If we just use the real data, we have only an intersection of a union of 9.67 for the welding spatter and 0.033 for the porosity, which is for sure useless. You can't rely on this good enough to use it for any kind of quality control. But if we step by step increase the amount of synthetic data up to 100% additional synthetic data, so we have 202 real images plus 202 synthetic images, then we can increase this intersection of union to a value of 23.44 for the welding spatter, and for the porosity to 28.02, which then makes it useful. And to be honest, in the most cases it will not be so relevant to localize a welding spatter the exact position. But we know now we have a more or less reliable result we can use to evaluate if this welding seam is good enough or not good enough. So in this slide you just see a little bit of graphical representation. It goes from right to left, stepwise increasing the amount of synthetic data which has been used for the second model, so the model which then does the real evaluation of the welding seam. And we see that on the left side we see the ground truth, and we see step by step, if we use more synthetic data, we get step by step more to the ground truth. This is in this case for sure not a quantitative but a qualitative way of looking at the results. So all in all, synthetic data can be used to compensate the lack of data, which is the main purpose why we use the synthetic data. And by the way, the aspect is not only that we now have more training data, also we have already labeled data, because the semantic mask which is used to produce the synthetic image is, in the next step, the label, the ground truth for the training process. Yeah, as you have also seen, the experiments show significant improvements in the segmentation performance when we combine synthetic and real data. And of course, the most benefit we will have for underrepresented classes, which is very often the case for failure parts, because you don't want to have failure in your production. And you, for example, if you have a failure rate or in the ppm range, it's quite difficult to get any kind of not okay data. And so this is, I would say, a real benefit to also introduce supervised machine learning approaches also in the field where these days it's difficult to get the right amount of real data. So then I'm more or less at the end of my presentation. You can also have a look at this demonstrator which I have shown in the presentation in hall 10 at the booth 10G45, and we can have the details discussions beside the questions you have perhaps right now. And if you want to get in touch, you can here also find my contact details. So thank you very much for your attention, and if you have any questions, I'm happy to answer.